In a real-time streaming conversational AI platform, every millisecond carries weight. If processing takes too long, the illusion of human conversation breaks entirely. This diagram illustrates our absolute limit, an 800 millisecond latency budget. If an audio chunk isn't processed and returned before that clock runs out, the response feels sluggish and the system fails. To hit that target, engineers often resort to wiring services directly point-to-point to bypass immediate bottlenecks. This creates what we call a big ball of mud architecture. This unstructured approach creates a network where the number of connections grows exponentially with every new service. Because the dependencies are undocumented, a single update in one node can trigger a failure in a seemingly unrelated component, stalling both system performance and engineering velocity. The alternative is applying proven architectural patterns. These are repeatable templates that dictate exactly how multiple components must operate and communicate as distinct runtime units. To survive the latency demands of real-time AI, we have to build a highly constrained, hybrid architecture from the ground up, because pure theory is useless if a system drops calls. Consistently hitting that 800 millisecond window requires ruthless structural intention. This shows standard 3-tier architecture: presentation, application, and data tiers. Adjacent tiers communicate via a client-server model. Data requests must process sequentially, never bypassing a tier. The vulnerability lies in the middle, where all business logic is housed in a single monolithic codebase. By centralizing every function, this single unit acts as a massive sponge, demanding vast amounts of CPU and memory just to stay idle. When we apply real-time AI constraints, concurrent audio streams instantly drain that centralized memory. Expanding the engineering team only accelerates the problem. Dozens of developers working inside the exact same codebase step on each other's toes, driving deployment velocity to zero. Processing thousands of concurrent audio streams, the monolithic tier cannot isolate resource consumption. Memory contention and thread exhaustion cause a total system stall. To protect that 800 millisecond budget, we have to completely dismantle this single logic tier and rebuild it as separate, independent units. We accomplish this by fracturing the monolithic logic into independently deployed, loosely coupled microservices. This design operates on Rule 1, the single responsibility principle. Every service is narrowly scoped to manage exactly one business capability. Take our STT streamer node. Its only job is to handle real-time speech-to-text conversion. It does nothing else. This strict scope provides essential fault isolation. If a malformed stream crashes a worker, the damage is contained. Adjacent services, like the orchestrator, continue processing calls without interruption. To maintain isolation, we adhere to Rule 2, a separate database per service. Sharing a database across independent microservices creates a hidden dependency. A lock in a central database takes down connected services, wiping out fault isolation. We accept data duplication across these databases as a mandatory architectural cost to ensure the units remain cleanly separated. Microservices secure our memory and active calls, but they introduce a new problem. We now have to figure out how these isolated units will quickly share information. If we wire these independent microservices to communicate through direct, synchronous requests, we immediately recreate the latency bottlenecks we just escaped. The solution is an event-driven architecture. We route all communication asynchronously through an intermediary event broker. Instead of services demanding immediate answers from one another, they simply emit an event, a permanent record stating that a specific action has occurred. With event sourcing, the system's state is stored as an append-only log of events. The rule is absolute: never delete a past event. If an error occurs, you don't erase it. Instead, append a new, compensating event to correct the value, preserving history. By decoupling the services that produce data from the ones that consume it, we maintain the strict operational isolation required to process our audio streams. Our microservices are isolated, but customer analytics dashboards still need to read data across multiple independent databases simultaneously. Running complex cross-database joins directly on primary databases creates massive friction. It hammers the critical write path and destroys our latency budget. We resolve this with Command Query Responsibility Segregation, or CQRS. This pattern completely separates the write path from the read path. Instead of querying the primary database, the dashboard queries a newly created separate node known as a materialized view. The system builds these materialized views by passively listening to the asynchronous event broker, pre-calculating optimized read-only ledgers designed to answer the dashboard's exact queries. Shifting the read traffic entirely to these specialized views relieves the burden, allowing the write paths to operate unimpeded. CQRS provides the necessary compromise, allowing us to support heavy system analytics without sacrificing the performance of our microservices. Assembled, this diagram shows our final AI platform, a strict 4-tier architecture. Top is the presentation tier, the customer app. Next, the ATI security tier via public gateways. Behind that, the application tier of isolated streaming workers, supported by the data tier's Postgres control plane. However, effective engineering requires knowing when to strategically bend the rules. For example, we made a conscious decision to violate strict microservice isolation by sharing our central Postgres database to handle billing. We accepted microservice coupling here because building a distributed database solely for billing logic would over-engineer the system and introduce unnecessary risk. Patterns like CQRS and event sourcing or strict microservices are not dogmas to be followed blindly. They are pragmatic, aggressive tools we deploy for one primary reason: to protect the 800 millisecond latency budget and keep the conversation alive.